So today we want to be focusing more on the formalization aspect of the problem. So I think in the talks yesterday really focused on a lot of the informal reasoning of kind of advances in language models. And earlier today there was some more emphasis on formalization. So just for those people who maybe haven't kind of thought about formalization or haven't even heard the word before. So this is simply the translation from human natural language of mathematics, of arbitrary software, into a formal machine verifiable code. And the activity of formalization, or the goal of formalization, has been a long-standing challenge in mathematics and more generally in software. And currently there is a community of formalizers who spend a lot of time and effort to do this work. But however, it's very technical and requires a lot of domain expertise, which is quite scarce at the moment. So there's some conferences, increasingly so among the math community, in Lean, which has gotten popular. But in general, this has been kind of rarefied skill that for pure mathematicians, we really are kind of relying on that kind of skill to help. And so as I mentioned, so up until quite recently, formalization has been very niche, and I myself only got exposed to the idea of formalization by a talk I listened to by Kevin Buzzard back in 2019, where he essentially kind of created this kind of social movement towards Lean. So he wasn't the first one to create the language. It was Leo DeMora earlier at Amazon. But he really kind of took on this kind of social challenge of really popularizing formalization among mathematicians. So previously there were kind of these landmark works of Tom Hales and others doing these large multi-year formalization projects. But recently there's been a lot of momentum among the math community in Lean. And in general, the formal verification does have applications. I think it should be mentioned for people outside of the math community because it's used for kind of reliability and reuse in kind of mission critical contexts where you really need to have certified code that works to given specifications. And so part of the work we're going to talk about today is acknowledged from this DARPA XMath program, which has provided us support. So in today's talk, I'd like to focus on one particular problem, the prime number theorem, and give some history for those people who are not necessarily in number theory or maybe don't have the context for the problem, and a recent challenge that was created by Terry Tao and Alex Kontorovich, which we're going to talk about today. And if time allows at the end, in spirit of the conference in the description, maybe we'll say a few words about what the kind of large-scale structure of mathematics as a whole might look like in the coming years.
Let's get to that part.
So maybe one way of phrasing some of the history is that in 1792, a young boy named Gauss noticed that the prime numbers have some interesting patterns that they get more and more rare as the numbers get larger. And in particular, he was just looking at a relatively small table of primes and observed that there was essentially a density of 1 over log x for primes, that the chance you take a random number of size x, it was roughly 1 in log x chance of being prime. And so he just noticed this from just looking at a small table. So today's maybe models, you would say you'd have like a very small training set and you're actually like observing a real trend. And in more modern formulation, the prime number theorem is kind of given a weight log p to kind of take into account this this density 1 over log x. So we have this weighted function, the sum over primes, actually prime powers, where we sum over log p, And the prime number theorem says that this sum is about the size x. So this is equivalent to the statement that the primes up to x, they're about x over log x of them. And the prime number theorem is one of these kind of central results in number theory that's really a foundation for a lot of results to come. So as some history, the prime number theorem was proven in 1896 by Audemard and Develay-Poussin, specifically in the following form, that this weighted sum of log p's, so we call it psi of x, is equal to x plus a small error term. So this is x over some exponential of the square root of log x. And so in particular, this is a quantity which is smaller than x. It's smaller than any power x over log x to the a. So this is more savings than any logarithmic scale, but it's weaker than, let's say, x to the 0.99. So it's weaker than a power savings. And if one could prove a power savings, please contact me after the talk. So in particular, their proof builds on these revolutionary ideas of Riemann. So Bernard Riemann was a geometer, worked his whole career in geometry. He won a single paper in 1859, an 8-page paper in number theory, which kind of set the field afire. And he built some ideas which led Audemard and Develay-Poussin to prove the following relationship between the distribution of primes and the zeros of the so-called Riemann zeta function. So in particular, that the zeta function is 0 whenever the real part of S is bigger than, a little bit bigger than 1 over 1 minus 1 over the logarithm of the imaginary part. And so this statement about the complex function zeta turns out to be equivalent to this fact about the distribution of prime numbers. And this result.
Maybe it's worthwhile saying that psi of x has a closed formula that literally depends on the 0. So it's not, that's not,
yeah, so there's an explicit
serious thing.
Yeah, so there's an explicit formula. You can analytically continue the zeta function. But
no, I'm saying there's a formula for psi of x literally in terms of the zeros.
The Riemann-Van Mangold formula?
Yes, Chebyshev formula. Some overwrote. Anyway.
Yeah. So,
not a mystery.
I'd be happy to talk more about the number theory, but just for the general audience, suffice to say that this was a real kind of culminating work that kind of at the time used the cutting edge tools of the day in complex analysis in the 20th century. And in fact, this relates deeply to the Riemann hypothesis, which was formulated in this 1859 paper, which essentially says that the location of the zeros of the Riemann zeta function are very precise. They're actually all lying on this line where the real part is equal to 1/2. And this is one of the grand challenges of mathematics. And Riemann was motivated by this conjecture because that of the connection to the distribution of primes, that if the Riemann hypothesis is true, this gives us an estimate for this weighted sum of primes with an even stronger error term. So essentially the square root of x. And this is essentially the best you can hope for. And so for this reason, the precise location of the zeros of the Riemann zeta function in the complex plane gives powerful information about the distribution of primes. And in the 20th century, Hardy famously asserted that the prime number theorem was such an advanced result that any proof of it would require complex analysis. And this was really set the dogma for the first half of the 20th century. But in 1949, it came as a great shock when Selberg and Erdős both semi-independently came out with an elementary proof of the prime number theorem, which did not use complex analysis. However, without using complex analysis, they were only able to prove a kind of weaker version of the prime number theorem, where you have some function, little o of x, so some function that is smaller than x. So if you look at that function divided by x, the limit is tending to 0. So this is a very weak form. And it's actually maybe worth noting that in more recent years, people have worked on getting stronger versions of elementary prime number theorem. But at the time, this was what was known. So with this as context, the prime number theorem has kind of been one of these results that in many languages people like to formalize as a kind of challenge. So notably in 2006, Jeremy Ottogod and a team proved the prime number theorem in Isabelle, the weak form of the prime number theorem, using elementary techniques, as in the Selbler-Gerdes proof. But recently, last year in January 2024, Terry Tao and Alex Kontorovich announced a project to formalize the prime number theorem in lean, and in particular, the complex analysis, the complex analytic proof. So this would not only give the result itself, but by building out the library of complex analysis, this would open up the way to work on other projects that depend on complex analysis. One of these kind of really important topics, but really has resisted some formalization attempts. And adds a very recent update so after about 18 months, just this past July, Alex Kontorovich and Terry Tao, they kind of gave us an amazing update that they proved essentially almost the same strength. They proved what's called what Alex is dubbing a medium strength prime number theorem, in which they formalized the statement where the error term is replaced by, so instead of having an exponential of minus square root of log x, they have a log x to the 1/10. So they have a kind of weaker exponent, but it was still, in many applications in number theory, this is often still strong enough to get nice results. But the kind of roadblock that Alex was mentioning is that this kind of found kind of a shortcut, a way to circumvent a lot of these core difficulties in complex analysis. So while many applications would be okay, maybe from a conceptual point of view, it was still maybe a bit unsatisfying to not get, for example, the classical zero-free region for the Riemann zeta function that was proven by Adamar and Devlet-Poussin.
Can I just ask a question about this?
Sure.
It's a little confusing because
Sure.
it's presented almost like, oh, we found like this new proof, this medium strength prime number theorem. But that I thought the whole point was like to formalize something. So did they find
No, this is a formalization
of some existing
yes,
proof
yeah,
of medium strength?
Yeah, exactly.
Yeah.
So I'm skipping a bit of history from 1896.
The tweet says it was just proved. So I understand that it means.
Okay, it was proved in lean, formalized in lean. Maybe there's some informal interpretation of that word proved.
I mean, you're still using the analytic continuation of the L function, right? And
yeah, so there's some kind of there's some intermediate properties of complex analysis that are used, but some of these core difficulties that are involved, for example, with the Borel-Carathéodory theorem, which in turn uses like the maximum modulus principle, there are a number of these kind of core results in complex analysis, which Alex essentially found a way to circumvent.
So he did come up with some kind of new proof.
Again, this is in the literature known to experts.
Oh, okay.
But that
it's not really the main part of the flow, the proof of the prime number theorem that you're probably thinking of, right? This is really
yeah. So people are always working for any important result, trying to find all the particular variations, all the different paths to a proof, and some of which are more famous than others. I don't think Alex is claiming that this is a new proof, but it serves the purpose for the formalization.
No, I get it.
Okay. So since July, just last week, we're announcing a new proof using a new agent, which we're calling Gauss, that proved the original goal of proving this quote-unquote strong version of the prime number theorem, which has the classical zero-free region and the classical error term x over e to the square root log x. And notably, this was the formal code was generated by a model, an agent we're calling Gauss, in a human feedback loop with me, the kind of local number theorist on the block. So in particular, so if you want to take a look at the code, it's available publicly on GitHub. And most interestingly, from my perspective, given the medium prime number theorem was in lean already, the kind of core, I think, novelty is actually taking the challenges in complex analysis head on and actually incorporating them into the library so that more results can be addressed. So for example, there was a recent conference I was at in June where Marina Vyazovska gave a talk about her efforts to formalize her famous results on sphere packing in 8 dimensions. And in particular, her work relies on a lot of these technical results in complex analysis. So hopefully, this kind of initiative shows that it is a proof of principle that it is possible to maybe contribute more complex analysis that will assist these larger other initiatives.
Can I ask a very small question?
Sure.
Yes, this is really great, but in the original tweet that you, or whatever you showed a second ago, it said also formalize the Chebotarev density theorem.
Yeah, so we're not
part of your project to do the theory and the Gauss theory. It's probably actually easier than the complex.
We'll get to we have not currently done so, but we are looking for future projects to work on. Yeah, so we're definitely interested in this, but today we're only making a announcement about the strong PNT statement. Yeah, question?
Feel free to punt this if you're going to comment on it in a few minutes, but could you comment a little bit on the extent to which having the human in the loop is part of the strategy versus something you're looking to get rid of in the future, and what the gap is?
Yeah, we're definitely going to get to that.
Thank you.
But essentially you summarized, currently there is a human in the loop, namely me, that at least the way I like to think about it is that I have through my schooling acquired some not only the kind of formal proof, but some intuition about the proof, and through natural language, the goal is to convert something into a formal statement. And the way I like to think about it is that there's a kind of mathematical structure that you're trying to preserve through some like homomorphism from an informal domain into a formal codomain. And the codomain has these nice properties that you can certify that things are correct, but you want to make sure that you're preserving enough structure. And right now, the human is very much in the loop to help with this, but we're actively working to decrease the amount of intervention that's needed. Okay, so maybe just as some context for this.
There was a result question.
Yeah.
Yeah, could you please go back to that slide?
Mm-hmm.
Yeah, when you say automatically, like automatically, like I was wondering, where did you start? Like, did you start from the very basic definition of a goal? Like, did you? Yeah,
so we have access to MathLib, so we're using a lot of the definitions that people have already contributed to.
No,
There's also
right definitions.
Mm-hmm.
Definition, you define where would you start for PNT and where you go next step, like this kind of blueprint. Did you start from there, or so
there's standard proofs in textbooks that we started from. So I took my graduate course in analytic number theory. I have notes from that, and we started from this kind of compact proof, and then with interaction with models, expand these informal proofs with my oversight. And once it's to a sufficient point that the model is happy, then we have the agent start to convert. But we'll get into more of the details. But just on the result itself, yeah. So we'll focus on the result itself, and then we'll talk about the methods. But just to give a sense of the artifact that is produced at the end of this procedure, so we have so in the medium PNT we have this nodes. So in the community, there's a notion of a dependency graph where each of the intermediate statements gets its own node. It gets colored green if the statement gets formally proven. And at the time, there were there's still stuff in, maybe related to Chebotarev density and other auxiliary results that are in other colors that indicate various levels of progress. And in this proof of the strong prime number theorem, we have about 25,000 lines of code in lean that was produced in 3 weeks, comprising about 1,000 theorems and definitions. And so historically, for context, proofs at this scale have historically taken a year or more, usually in a group of human formalizers. and each of which have kind of been a major a milestone. And yeah, so also for context at this scale, so a few months ago in June, we announced Trinity at a conference in Cambridge, which was about 3.5, so about 3,500 lines of code, proving a old result of De Broglie about the ABC conjecture on average. And itself, so this is about an order of magnitude difference from today, from June. And that itself, 3,500, was already about an order of magnitude larger than prior automated efforts. And so the largest formalization projects that have ever been done in any language, so these are about maybe 500,000 lines of code. So think about the Kepler conjecture by Tom Hales, also like the odd order theorem. These sorts of massive undertakings, which I think in some instances can span more than a decade, are probably around an order of magnitude larger than the current project. And even further, so MathLib, the library for all of Lean that had been compiled and coordinated to make interoperable with many results, is only yet a magnitude larger. So it's about 2 million lines of Lean code, which comprise about 350,000 theorems and definitions, which was compiled by hundreds of maintainers and contributors over about 8 years. So this is just giving a sense of proportion about the scale of this work, which is about order of magnitude smaller than the largest projects and 2 orders of magnitude larger than MathLib. So before getting into the kind of aspects of the agent, I also wanted to stress maybe some interesting kind of progress along the proof, which some of which was not already evident in the textbook proof, which so for maybe those of you who've heard Emily Riel, she talks about the notion of invisible mathematics, the idea that when humans are conversing with each other, especially those in the same domain, they take a lot of assumptions for granted, and they can kind of move faster and in a more compressed way express what they want to. But one of these kind of key results in complex analysis, which was crucial for the proof, is called the Borel-Catheriori theorem, which essentially says that if you have an analytic function and you have a bound on its real part, then you can get a bound on its modulus. So maybe a conceptual way to think about this is that for an arbitrary complex number, it has a real and imaginary part, which are just independent of each other. However, if you're imposing the condition that a complex number is the image of some analytic function, so if you're looking at some nice complex numbers, then the real part and the modulus, or in other words, the real part and the imaginary part should be related. So one should be kind of roughly bounded in terms of the other. But I should also emphasize in this statement, there are actually some subtleties which actually turned out to be quite kind of important to keep track of in the proof that was not mentioned in the textbooks. So for example, we have these 2 radii, a little r and a big R, on which our function f is defined on a large disk of radius capital R, and we're assuming a bound, so we're assuming that f is analytic and it's bounded by m, the real part is bounded by m on the small disk of little r, radius little r, and then you get to inherit these bounds. And moreover, there's a kind of another argument involving the Cauchy residue theorem that allows you to deduce from Borel-Catheriori a corresponding bound on the derivative of f, assuming the real part's bounded. And in the prime number theorem proof, we actually apply the Borel-Catheriori theorem, where our choice of function is the logarithm of the zeta function, actually a shifted zeta function. And the kind of observation here is that if you take the derivative of f, so f prime, here you get zeta prime over zeta, which is, yeah, exactly. So you get this kind of key sum over prime powers. And this also motivates the definition of looking at prime powers. So a lot of these kind of implicit results here ended up using very basic theorems that were actually not in MathLib. So looking at even multiple sources subtly, this is just kind of assumed as the water you're drinking. Where, for example, I mean, this would be mentioned maybe in a graduate complex analysis textbook, but nowhere in an analytic number theory proof that you needed your function, if it's analytic on a disk, then it has a primitive, it has an antiderivative, and that it has, therefore, a complex logarithm where you can do this procedure.
Did Lean identify this issue for?
So it was identified that there was an obstruction, and the agent comes back with the suggestion that this is the kind requisite property that we needed. And so because of that, there is a conversation in which the agent comes into obstructions, and that forces me to revise the informal blueprint.
So it actually, Gauss provided on this new idea of meeting these basic theorems that weren't in the textbook.
Yeah, so
it gave you some useful back and forth. It wasn't just.
It's sometimes very painful. I mean, some of these technical issues, I also want to mention with the various radii, you actually have to apply this not just with this function f itself, but there's also an auxiliary function called the Blaschke factorization, which is related to f, where you divide by the zeros of f. So like, maybe I'll even write it here. So for a function f, you can define b of f as the function times, well, you first divide out by a lot of the zeros. So, and maybe it's only for zeros within a given radius. And then you also do something kind of, something like this. So you have some auxiliary product, which looks kind of ugly, that you also need to manage, which itself introduces two more radii, which you have to keep track of. And in particular, the radius here are two different radii, which I should say when I saw the proof of the prime number theorem in my graduate course, and also when I was a TA for the course, my eyes would always glaze over. Like, this is a section that you just have as an appendix, just to like, satisfy, the people who are maybe emulating some lean compiler in their head that really want to have it. But just like conceptually, your eyes always glaze over, and you kind of forget about these details. And really, interacting formally with the proof really forced me to understand that, number one, we actually need to use 4 different radii, which is never mentioned in kind of the informal proof, and also kind of motivating why, number one, you have to divide out by the zeros, and you have to multiply through by this also other factor to make sure that the modulus gets preserved. Like, this is something I never really kind of paid attention to, but it was just an interesting kind of piece of education.
Can I re-ask this question? Because
Yeah.
I think it's really essential to like understanding where you guys are at. There's a difference between translating known things that are in textbooks and using these tools to really extrapolate in new directions. I guess what I want to ask is some sort of quantitative thing, which is like the probability that you have to intervene on the translation task versus these types of, even if they're basic theorems, if they're new theorems that aren't in textbooks everywhere.
No, but I should say that all the results are in some textbook. They are not in the excerpt on which I constructed my informal blueprint.
So
But these are all standard results.
I
Just to be clear.
One of the interesting questions, if you have a comment moving forward, is like how much more do you have to intervene on something that's truly new versus something that is in the core?
Yeah, so that is very much an open question. It's very much an empirical art at the moment. And also there's been a discrepancy in the result I mentioned back in June for the ABC on average, where the proof here actually required quite substantially less intervention. So
Wait, say that again? Which one?
so over time there's less intervention.
Oh, but that's, I see, you're not, go on.
Yeah. So and we'll open up to discussion, but I just wanted to emphasize, oh yeah, before getting onto that, I just want to emphasize that yes, there is certainly human feedback in the loop, and it remains an empirical question, the degree to which this is, the rate at which this is decreasing over time. I also want to mention that in the development of the agent, we relied on key infrastructure developed by so-called Trinity environments in partnership with Morph Labs, which provides a way to scale lean verification to a large scope and operate in parallel with many agents. And in general, this is a serious, systems engineering challenge. Sometimes several thousands of concurrent agents, each with its own lean runtime and a lot of memory. This is not my, I'm not by any stretch of the imagination complex systems engineer. This is other people on the team, but this is provided by what's known as Infinity Branch, which was definitely critical to the success of this effort. So just as a kind of quick comment, and then we can maybe get into some further details. So Gauss is really meant to kind of advance the kind of scale at which we can do formalization, have large scale collaborations. So maybe for some context, maybe in the past 10, 15 years, people have been working on these polymath projects, which is a way to kind of open crowdsource mathematical collaboration, not necessarily for formalization, but just collaboration in general among many people who don't necessarily know each other. But the advent of formalization also offers a certification of guarantee that you don't actually have to trust the people you're collaborating with. So it also opens up the opportunity for larger scale collaborations like this. And we anticipate, again, the current form of Gauss to be changing over time, especially in the coming months. And we're pushing for greater capability and autonomy. So we'll be beginning to deploy Gauss to make it useful to people in the community, both formalizers as well as mathematicians who themselves don't really necessarily know formal code, but are interested in having results they care about get formalized. And presently, we're in contact with an initial group of mathematicians working on potential interesting projects. And if you have an idea for an ambitious project that you would like to contribute to be a beta tester, you can register at our website, as well as career opportunities for people interested in contributing. So maybe I hope maybe this gets to maybe answering some of the question about for mathematicians who have spent many years in a particular domain and really have a conceptual understanding informally of mathematics that they care about. This should open a new, maybe new mode of interaction where one doesn't necessarily need to actually write the code themselves, but as long as they're interacting with a colleague, this time maybe an automated colleague, to assist with the formalization and give feedback. So this is maybe what I'll say on here, and I can open up to questions. But really, we're trying to push towards a view. So there's a famous book called Category Theory for the Working Mathematician. So this is a sense in which category theory is this one domain where it has lots of powerful implications, but maybe not everyone necessarily gets into category theory themselves. By the same token, we kind of view this as a step towards having formalization accessible to a lot more people who are themselves investigating Lean or other formal languages. And so we're trying to open up tooling to the community in order to kind of massively scale up the amount of formal Lean code that is produced from 2 million and beyond. And so maybe in the spirit of the remaining kind of time, I'd like to talk about just philosophically where I think we're heading. So the enterprise of making formalization is a way to have kind of some certification, some sense of mind that the results we have are correct. So there are many examples. I think most close to my heart is an example of Vladimir Voevodsky, who was a real genius and expert in algebraic geometry, algebraic topology, who had proven many results, which over time people were impressed, but became more and more obscure that no one else was really verifying his results, and people were just checking, relying on his say-so. But over time, he realized that he actually made a critical error in one of his papers that was pointed out by one person, but he dismissed it. And then over a decade later, he actually realized that there was an issue that was legitimate. And because of this, he really had, I think, a philosophical turn, and he decided to actually get interested in formalization. A lot of the efforts in Lean are very much, at least to me, inspired by this line of thinking. And so really what formalization is meant to do is really to give a check on, I think in mathematics, we really pride ourselves on not having, relying on trusting experts based on their word, but really having some sort of hard guarantee and hard verification. And one of the things I like to think about over maybe the history of maybe formalization, even before computers, we had the group Bourbaki, who were constructing this large pseudo-formal database before, so pre-digital formal database of mathematics. So if anyone reads these textbooks for Bourbaki, they're really these thick tomes that no one is really meant to learn mathematics from, but they really represent a very compact, compressed unification of all the mathematics that was at the time. And by the same token, we don't necessarily expect people, human beings, to necessarily engage with the formal code that we end up producing, but we rely on it as a way of having kind of a single unified artifact that can be built upon. And I should also mention that maybe conceptually the way I think about it is that over time, the practice of mathematics is always expanding. We're always proving new results, and over time we get increasing specialization. So there's a famous interview with Michael Atiyah who talks about the kind of miracle, how after every generation of new mathematics being produced, the next generation can take this results and actually continue and absorb and synthesize what is existed. And he left it as an open question whether this can continue. Or whether there'll be indefinite specialization. And really, so the way I'm kind of thinking about this enterprise of large-scale mathematics in the future is that we have these two competing objectives, these two objectives in tension, one of expansion, of proving new results and exciting theorems, and the other of contracting and compressing the existing knowledge base we have so that it might be usable and understandable to whatever participant is working. And the way we should really kind of envision mathematics, regardless of human or machine or collaboration, we should really regard the basic activities of mathematics as really working in a code base, a code base which to many of us in the audience is near and dear to our heart, which we're always trying to either expand or we're trying to refactor it and make it more unified. And regardless of what the next number of years holds, I think those two basic goals of expansion and compression are going to remain with us. And so with that, I'll leave you guys.